I will go ahead and introduce our next speaker. Isan is giving the talk called Migrate from Hive to Delta Lake. And just very quickly, while Isan starts to share his screen, Isan Liu works as a senior software engineer at Amobi. Previously, he was working on Amobi's data warehouse system, DataMine. Now he and his team are building a next generation data lake on top of Delta Lake. Isan is a graduate student at Carnegie Mellon University, where he studied distributed systems and databases. Isan is also a contributor of open source Delta Lake. So Isan, whenever you're ready, you can take it away.
Yeah, thanks, Anya. Can people see my screen?
Yes.
Okay, cool. Yeah, nice talk, bro, Neil. Yeah, so I think it's my turn now. And welcome, everyone. I'm Isan Lu. You can also call me Isan. And today I'm going to talk about how we migrate from Hive to the open source Delta Lake and Hive. All right, so let's go next slides. Okay, so what can you expect from today's topic? Today, I'm going to talk about Amobi's data lake and why we need Delta Lake. And second, what the challenges we met when we adopted Delta Lake on productions. And third, what the solutions we come up with. And at the end, I will go through a simple case study. Okay, who am I? Obviously, we can skip these slides. Thanks, Anya. You saved me a lot of time. So as a routine, let's start with Amobi. So Amobi is a leading independent advertising platform and unifies all the advertising channels, including the TV and digital and social. Basically, we provide one-stop solutions for the converging world. And one of the challenges in the platform data team here is we will get the data from different data sources, and the data size of tables can vary from the terabytes to petabytes. And we really want to build a generalized data pipeline architecture to support the different use case. And as we all know, there are many frameworks outside there you can choose, and you can use Spark, you can use the Hive, and so on. And what to choose? And this is a diagram posted at one of the meetup before. And as you can see, Spark is the multi-purpose execution engine. It plays important roles in many different areas, including the SQL, execution, machine learning, etc., streaming, yeah. And also, Hive is an industry standard. It offers a centralized place to manage the, okay. I was checking some chat. Okay, it offers a centralized place to manage all the tables. So it will be a very complement for the Spark. And how does our data lake looks like? So at the end, we build our data lake on top of Spark and Hive. So it has several components, though the first one is the data pipeline service. So we set up a generalized data pipeline service on top of Spark. And how it works is it can read in a configuration, and it will use the flexibility of a Spark API and all those things. It can just set up a new pipeline. So it's quite complex. It's quite generalized, and it can read a lot of data, different kinds of data. It can reuse many Spark lower level API. And the second thing is we need to have a catalog service to manage all those tables. It can be like hundreds of tables in our production, and we need to manage it. So we build an independent data catalog service on top of Hive. And also sometimes you have data in different geolocations. You have data in the cloud environment, you have data on premise. So we have a requirement. So we need to transfer this data across different classes, different environments. So we have a sync service to help this case. So something you might notice, there's a snapshot component in this architecture. So this is actually a snapshot-based pipeline. And what is snapshot? So snapshot is a group of input files. So we have split all the files into different groups, and each of this group or each of the snapshot will have a unique snapshot ID. And how does it help for us? So the snapshot-based ETL actually gives us a better management on the input and output files. It works pretty well in the production. It gives us the data lineage between the input and the output, and also each ingestion or each ETL on this snapshot is idempotent. You don't need to worry about, say we have the same snapshot or same files got processed multiple times, and then you might have if you use the Spark API directly, you are going to have a duplicate data, and basically your data lake is messed up. So, and later we will see how this snapshot concept is used in the Delta Lake. And all of this works pretty well. This architecture works well for many situations, but at the end, we found out some issues. So there are some overhead at the catalog service side. The catalog service had a hard time dealing with some big and wide tables. And after we dig deeper, and we found out the limitation actually come from Hive. So what are the limitations? So there's a long start time for Spark query on the join tables. And when we querying the Spark, how Spark works is, let's say we have a query, it comes in. And then the Spark needs to get a partition list from Hive first. And then it will go through those partition folder, and it will scan in all those files, and then set up an execution or planning, set up an execution plan. And this is going to be terribly slow, especially the table have hundreds of thousands of columns, hundreds of thousands of partitions. And the second thing is it's hard to run a DDL on a wide or join table. So we have a very big table in production. And then if I want to drop this table, first what we need to do is we need to drop most of the partitions in this table. Why is that? Because the Hive meta store is the bottleneck. So it cannot handle this use case. And if we need to add a new column into this join table, it's also going to be terribly slow. And the third one is there's no native support for the upsert and delete in Spark. So basically Delta Lake is designed to address this issue, these limitations. And at the end, I guess many people might have headaches on this. We don't have, for Hive external tables, we can only track the changes at the partition level. So we have no idea about what changes happen within the partitions. So why is that? Because the partition information and the files, they actually are stored in two different places. For the Hive external table, the partition information is stored in the Hive meta store, is the database. But the files under the partition is stored in the file system. So there can be chance we have a consistent state. So someone delete the files in the partition, but the Hive won't be able to know. Okay, so this, we have a Delta Lake. So Delta Lake is designed to address above limitations. And what is Delta Lake? According to the definition from official website, Delta Lake is an open source storage layer, or we can also call it a table format. So it brings in the ACID transaction to Apache Spark and the big data workloads. It has many good features for a modern data lake. And I would say the most important thing that attracts us is there's no vendor locking for the open source Delta Lake. So the Delta Lake won't change the data you store in Hive. So if you don't like it, you just drop the table and recreate again. So there's the minimum risk. So how does Delta Lake implement all above features? So it won't change data, but it comes with so many good features. How does Delta Lake implement that? All the magic actually happens in the transaction log. So what is transaction log? Transaction log is the folder, or we can say the transaction log is stored in the Delta log folder. And this folder lives next to your Parquet data. And as you can see on the left side, the transaction logs are stored in different JSON files or Parquet files. And each JSON file is actually one commit. And for every 10 commits, the Delta Lake will create a checkpoint files. So as you can see, it uses the Parquet data here. It will scale with the cluster. And all the information about this table are stored in this transaction log. So it has a better scalability than the Hive meta store, because Hive meta store is just a singleton. is a database. So also, what's inside this JSON file, or what's inside this transaction log? And there are actually mainly 3 types of the metadata stored in the transaction log. Or we can also say there are 3 types of actions in this Delta table. So the first one is the metadata. And it defines what the tables look like, and then what the schemas, what the type of the column, etc. And the second one is the add file actions. So it tells you, okay, what files is added into this table. And the third one is a remove files action, and what file is removed from this table. So let's just go through an example and see how Delta Lake use this one. So let's say we have a Delta table, right? So how do we define this Delta table? We can define this Delta table by 2 commits. So the first one is we're going to define the schema first, and then the second one is going to be add file operations. It will follow by add file operations. We're going to register all the files into this Delta table. And what if we want to update this table? What if we want to delete a row from this table? Right. So let's say we have a row that is stored in the myfile2 on the left side. And how the Delta Lake works is we submit the command, or we make a call to the Delta Lake API, and then the Delta Lake will scan the file in the Delta transaction log. And then it will remove the row in the myfile2, right? Let's say this row is in myfile2. And then it will remove that line and write out as myfile3. So since like we already have the data got written out, so in Hive the work is done, but actually in the Delta Lake, it relies this metadata or this transaction log to tell the table what files is inside the, what file is under this table, right? So you still need to make another commit 3, and tells Delta Lake or tell the Delta log, say, okay, I'm going to remove my file 1 because this is old data, and I'm going to add my file 3, and this is the new data. Okay. Okay, so with Delta Lake, it solves most of the, address all our above limitations, Hive limitations. So you can have a faster Spark query planning time. So the Delta Lake, instead of reading the partition information from Hive method store, and the Spark, it will read the schema information, will read all the files from the transaction log. So it has a higher scalability. And we will talk about how the performance looks like in the next few slides. And the second thing is it has a faster DDL on the dry and white tables. So all the changes to this Delta table will be appended. Okay, it will append as a new commit into the transaction log. But in the Hive world, what will it look like? So in the Hive world, we need to know, okay, what's the target schema I'm going to use, and then what's the latest schema in Hive, and we need to compare these 2 schema, we need to generate the alter command, and then we need to run it. And that's how Hive works. And all it's saying is going to be slow on the giant table. Okay, so the next one is the upsert and delete. So the Delta table will bring in, upsert and delete features. And it is pretty useful for the GDPR and CCPA use case. And at the end, all the files in the Delta table is managed at the file level. So which means you don't have those mysterious things happen inside your partitions. And all the output files is recorded into the transaction log, right? So everything looks good so far. All the features bring by the Delta Lake can solve our problems. And however, when we try to use this Delta Lake on production, we found some gaps. And what is missing? So there are several things. So the first thing is there's no easy way to update transaction log. So Hive offers a pretty comprehensive API to get all schema from existing table, and it's make it very easy to run a DDL when it is required. But however, with Delta Lake, you cannot get schema from the transaction log easily. Instead, you need to go through the Spark API, you need to read the table schema, you need to launch a Spark job. Especially launch a Spark job is very expensive in this case. And also after that, you need to run the DDL. And the second thing is there's little control over the output file names. So why we need that? because in our this snapshot-based ETL or pipeline, each ETL process on a single snapshot is idempotent. So this is implemented by the control of output files name. So, but there's no easy way to do this in the Delta Lake. If you're reading the same files and then you write out several times, are going to end up into different files. So you will have a duplicate data into the Delta Lake. So how to solve that? And for the first one, we introduce a Libby into our existing catalog service. So the catalog service will offer a RESTful API so that you update the transaction log easily. You can do the add files, you can do remove files, you can also up the schema through this RESTful API. And the Libby is the one who maintains this Spark or Spark sessions. And the second one is, if we want to control the output file name, we cannot use the higher level API because it's going to write out the duplicate files. So, sorry, it's going to write out different files, but we want the file name to be the same. So instead of using the Delta Lake save ID directly, we leverage some lower level Delta Lake API to commit the files by ourselves. So we can do the add file, remove file, or schema updates through our own API. And in order to make our snapshot data processing idempotent, the output files of one snapshot will always commit together. So at the end, what will be the snapshot? What's the relation between the snapshot, pipeline, output files, and the commit? Okay, so this is how it's going to look like. So as you can see, the output file for one snapshot will end up into one commit. Then we will have this snapshot level lineage and the snapshot level idempotent commit. And this is pretty useful later in our case study. And the third challenge is the slow table conversion. So after Delta 0.4.0, Delta Lake introduced an API to help us easily convert an existing Hive table into Delta format. And the performance is acceptable for small table, but actually it works poorly for the big and giant table, especially on some cloud environments. So to improve the performance of table conversion, we implemented our own tool for converting the table into Delta format. So the table, actually, the tool is similar to the Hive. So first, we will define the schema of a Delta table, and then we will follow by a call to our implementation of MSCK in Delta Lake. So how does MSCK works in Hive? So the MSCK in Hive is used to recover the partitions that shows up on the file system, but not in the Hive method store. So it will scanning the file system and then find out, oh, these are the partitions, and compare what we have in the Hive method store. And then insert the partitions that doesn't exist, or remove partition that doesn't exist anymore. So this performance is acceptable for small table, but again, for giant and wide table, it performed pretty poorly. And we can borrow this idea from the Hive, and then we implement the same thing in the Delta table. So Delta Lake itself has a very good API to tell us, okay, what files is inside the transaction logs. So what we need to do is we build a scalable way to scan the files on any file system, including the cloud environment, including the on-premise environment, etc. So combining these two, we can do one thing. We can commit those unchecked files on file system into the transaction log through this API. Okay, so let's say we have a new tables. What we are going to do is, we are in the catalog service side, we will commit the schema first, and then we will run an MSCK after that. So we did a simple test on our use case. So we have a table that's around 100 terabytes of data, and it has more than 100 of columns, and have millions of files. So the MSCK in Delta Lake works pretty well, especially for our own API. So when we try to convert these tables into Delta format on cloud environments, actually, it only takes 2.5% of the time compared with the native API, the native Delta Lake API. And it's also performed very well on our on-premise environments. Okay, you might also notice there is a 2NA in this form, which means it's not available. What does it mean? So it means if we want to drop or query a join table without specific tuning, it will take a lot of time to finish. It won't even finish in the Hive. Okay, so let's talk about the rollback feature. So this feature is actually ported into the commercial version, but it's not in the open source version. So, but it's very important for us. So if there's something going wrong with our data lake, we want to have a way to perform a one-click rollback. We can click, we can roll back to specific versions, and we will have a healthy state. And the next one is it's very slow to get the table properties. So the Delta Lake support table properties, but again, you need to access through the Spark. So it's going to be slow to start a Spark session. So we decided to store those important properties into the Hive method store. Okay, so, but how do we address the rollback features in this case? How can we have a rollback features? So to support the rollback features, we actually implement our own versions. So as you can see here, let's use an old example. We have a table 1, and inside this table 1, we have my file 1, my file 2, and my file 3. But we found out, oh, something wrong in our previous case. We have accidentally removed one row from my file 1, but we want to roll back. We don't want to have these changes. So how can we do that? So it's pretty simple in the Delta Lake or in Delta table. So what you need to do is you just need to comparing the commits between version, let's say version XXX and the target version. And then you can do a rollback commit. So in this case, we will do a rollback commit, we'll do a revert commit, we will add my file 1 back, which has the correct data, and we will remove my file 3 from this Delta table. Then we will have a healthy state, healthy tables. Okay, so the 6th one is there's no cross-cluster Delta Lake management. Your team might need to build a data lake in different environment according to your business use case. It can be on cloud, it can be on premise. And the data will distribute it in different geolocations. And it's also important to keep the data integrity across this environment. But there's no cross-cluster management in the Delta Lake. So at the end, what we are looking for is we want the data on different environment need to be the same. We want the changes of the data need to be the same. We also want the order of the changes need to be the same. So at the end, we can have this exactly same data table across different environments. So with Delta Lake, we have designed this master and slave architecture for each Delta table. So all the write will go to the master cluster first. And then once we write it into the master, so there can be some time like the slave cluster is behind. So it can be behind like 3 versions or 4 versions, 3 commits or 4 commits. So how can the slave catch up? So with this sync service, it makes the life easier. So what we need to do is we just need to find out, okay, what new files are ingested between this slave version and the master version. Let's say in this case, master is at version 6 and the slave 1 is at version 2. Then we can use the Delta Lake API to fetch what files is committed between these 2 versions. And then we do the copy. So the data will be copied first. If it succeeds, then we can start to copy the commits or the transaction log. And at the end, they will be in sync. Okay, so with this master and slave design, it also helps us to monitor the table easily across different clusters. We will know, okay, between the master and the slave, how much behind the slave cluster is comparing with the master. So as you can see here, we have how much version is behind and how long the commit time is difference. Okay, so at the end, we have this new architecture. So after we introduce Delta Lake into our pipeline, you can see the change is not that big. The change is not that big. What we need to do is we just need to introduce the Delta Lake libraries, and then we need to add the Levy into the catalog service, and also we need to have a sync job to sync data across different clusters. So let's do a simple case study here. So we can see how the Delta Lakes works with our snapshot-based pipeline. Assume there's something going wrong with the input. So some duplicate data is ingested into our data lake. So the file list in different snapshots is supposedly to be exclusive, but at this case, they have some overlap. So right now, because the pipeline already finished and you have some duplicate data got written out and the table is in a massive and unhealthy state. So how can we do the rollback? So with this Delta Lake API or this Delta Lake design, we know the data lineage between the snapshot of output files and then with snapshot of input files, and we know the commit. So what we need to do is we just need to use the snapshot ID to do a one-click rollback. Then the table is back to an older version, but a healthier state or clean state. And at the end, we fix the issue and we can regenerate the snapshot again and rerun the pipeline. Then the table is back to the healthy state. Okay, so what we are looking forward to have in the open source Delta Lake. So we know there are some difference between the open source Delta Lake and the commercial version. So what we're looking for is we want to have a compaction which will help us to speed up our queries. And we're also looking forward to have the query optimization introduced to the Delta Lake. So in that case, we will feel, okay, Delta Lake is a more matured and a better table format for us to use to address the Hive limitations. And here are the reference of my presentation. We have wrote a blog to explain about the design, and just feel free to check it out. And at the end, we'll have the most important slides, Q&A. And by the way, we are hiring.
Awesome. Thank you so much for a great talk. We do have a couple of questions in the Q&A. So I will just read the first one out. This one comes from Frank. The question is, can you please elaborate on why the JSON file-based transaction log used by Delta Lake is more efficient than the MySQL-based Hive metastore?
Okay, yeah, so this is a good question. So as I think I explained a little bit in my slides, but I can repeat it here. So Hive, MySQL in the Hive metastore is a singleton. So what happened in our production is when we try to use a very joint table, when we try to query a joint table, it takes a lot of time. It spends a lot of time at Hive side. You need to push down the filter. You need to know what partitions to fetch. And then other than that, you also need to go into the HDFS folder or the file system and then scanning all those files. But in the Delta Lake, all those information, the schema, the files is always written, is already written at the write-out time, or it's already registered. So instead of using the Hive database, MySQL database to do a query, so how Spark works is Spark will reading this Parquet file, will reading this JSON file, and then it will know, oh, this is going to be the table, or this is going to be the data, or this is going to be the files I need to use. So as you can see, it's running in Spark, right? It's distributed. So it's more efficient than Hive than a singleton. Yeah, I answered the question.
I think so. I think that answered the question. Frank, feel free to chat further on that question. You can make comments on individual questions. So yeah. If you could talk a little bit more about schema evolution in Data Lake. So Mike has a question. How does schema evolution work in Data Lake? For example, what do we do when we are ingesting Avro files and storing it in a blob storage, and the data provider makes a change to the Avro schema?
Okay, yeah, I think, so this is the good question. So according to what I knew so far, so the Delta Lake only support the Parquet data. So all the file formatting to be a Parquet. I think they might have planned to support a different use case or different file format in the future. But I can also talk about how the schema evolution works in the Delta Lake. So Delta Lake itself has an API. So let's say you store your data into the Parquet format, right? So, and also this schema is defined into the JSON file or into the transaction log. So the Delta Lake offers a good API for you to check, okay, whether my current data set can be written out without any issue. So you can compare the schema inside the transaction log with the schema of your data set, of the data set that you want to write out. So if there are some issue, then it will throw exceptions. So we can, in this case, or you use this API, you can easily know, okay, whether there's something wrong with my schema, if the schema is backward compatible, etc.
Okay, great.
Mm-hmm.
Let's see, there's a lot of questions, a lot of interest here. We do, it's great. We do have we have 5 more minutes to go through the Q&A, so that works. Another attendee is asking, please share some metrics around performance, and let him know if you've compared or benchmarked these queries against GPU or CPUs by any chance.
Yeah, sorry, we are not using GPU here. We're only using the CPU.
Okay, great. Mahesh is wondering, which catalog tool are you using?
Okay, so yeah, I think I can share something here. So we built our own catalog. So this is a catalog service, and so how does this catalog service do is we have a schema that passes around our different service, and then this schema can tell us, okay, what's the target schema I want to use? Let's say there are one more column is added, there is one more column is removed, and then what catalog service works is we build our own catalog service actually. So how does it work is it will accept this schema information or this schema file and compare with what exists in the Delta log or in the Hive, and then did the corresponding update, right? So we don't use any like specific tool. We build our own catalog tool.
Okay, awesome. Another question, maybe you can scroll back to the beginning of your talk if you don't mind. The question is, what are the solutions that you're providing that would be out of scope if the user just wants to use the non-open source Delta?
A summary of which solutions you are providing are not necessary. Okay, I think Rollback. So Rollback is implemented by ourselves, but as far as I knew, the Rollback feature is supported in the on-premise version. Sorry, the commercial versions. And another thing is will be I don't know how the commercial version manage the data across different classes, because for our case, we need to manage this Delta Lake across different cluster, and then we need to save some like processing time, or we also doesn't want the computing resource to be used up. So we will have this master and slave relation, and then master and slave architecture, and then all the write will write into one locations, and then we'll copy the data to another one. So I don't know if this is also supporting to the commercial versions. And other than that, yeah, I don't think any other solution is any other solutions are implementing in the non-open source Delta. But I'm looking forward to have the query optimization and the compaction. Those sounds very useful, because especially there are so many table format outside. There's Asberg, there's Hoodie, and recently Hoodie become a top level project, and all of this try to address the Hive issue and yeah, the Hive limitations.
Great. It sounds like you've given a really nice overview of the challenges that you faced and also potential solutions for each of those challenges. So the format was really great for our audience. Thank you so much. Clearly, a lot of interest in both talks. I'm going to share my screen. Let's see. I think everybody can see my screen. So I just want to thank both of our speakers, Neil Conway and Isan as well, for giving 2 great talks. And a big thank you to AI Camp for letting us, for enabling us to do this online and meet all of our attendees where they are. For those of you who are looking forward to our next talks, I know I am. We've got a couple of great talks coming up. Productionalizing big data talks from Lyft and Workday, a scalable experimentation platform. So that should be interesting, especially considering the determined talk, to see some comparison there. Thanks to our panelists, thanks to AI Camp, thanks to all of our attendees. And I guess we'll close it up there and we'll see you next time. Thanks, everybody.